Okay, so let's start. I don't actually remember nicely what was at the beginning of the subchapters, so I will try just recall in live that
He
those.
basically just talked about that the classical quantum systems doesn't account for relativity because the time ticks at the same rate for every particle. That's well, it doesn't fit with relativity, of course.
Yeah, so I have a few notes here, and probably I will open video for myself to see it full screen. Okay, so the first one starts with quantum mechanics of many particle systems. Okay, and what we have here. So at the beginning, Penrose talks about previous chapter mathematics, and is it good enough for, like, he just like asks a question, is it good enough for a few particles actually? And he says the answer is no, because of quantum entanglement. Yeah, and identical particles, particles that are identical to each other, he says, always automatically entangled with one another.
Yes, I had a question about what does he mean by identical particles? Do we know this?
I think that he means like family of particles, like bosons, fermions, or something. I don't know, like all of the electrons they are entangled somehow or something.
Because there is one thing about quantum where every particle in the universe is basically the same. Yeah, I can't recall it now.
That's I think you are talking about Feynman's theory.
Probably, yeah.
Yeah, he has like one electron theory years ago.
Yeah,
Is
yeah.
anyone hearing
That sounds right.
Slava's mic is really scratchy?
Yeah,
Yes, it is now.
yeah, I hear that too actually. Maybe turning off the noise reduction will help. Maybe it is better now.
Yeah, it is.
Definitely.
Okay, probably it was noise reduction filter. Yeah, so we were talking about the Feynman theory about one electron, but I'm not sure about this thing about entanglement of the same particle. Maybe John knows something about that because I never heard about that fact before.
Well, all I know about like identical particles is just that they have the same quantum numbers, right? It's just an electron is identical to another electron. And the way that you would determine whether they're like distinguishable or not is if they differ on a particular degree of freedom. So, like for example, indistinguishable particles would be like two electrons that are sitting in a potential well or something, and then for distinguishable particles that would be like two quarks sitting in that same well, and the difference would be that basically all the spin content of them is the same, but perhaps they're distinguishable because they have a different color charge, like maybe one is red and the other is blue. So usually identical particles is not really a major distinction, but distinguishable particles is a better distinction.
Okay, but I think that's like that small sentence here is not like the main one. Like maybe it's just a glance or like running forward a bit to the like particle theory or maybe standard model. I don't know. Yeah. So anyway, maybe that will be discussed later in chapter 23. So I think that's just like a preview what is ahead of us.
I think I know what he's talking about here. So what he means that they're automatically entangled, like at least in the case of fermions, like two electrons in a box. That I think what it means is that if they're identical and indistinguishable, then they can't be in the same state. That's like that's a Heisenberg principle. Or I'm sorry, not Heisenberg, but Pauli exclusion.
Pauli
Pauli
principle,
exclusion
something.
principle. That's the one I was meant to put.
So yeah, I think that's what Penrose is talking about here, is that they're automatically entangled, because
so
if you
for fermions,
if you know
they
the
kind
state of
of
one,
so they're connected in terms of their states. Like one state of the one particle implies the state of the other one.
right? And then if they're distinguishable, like I said, if they differ on some other degree of freedom, then the exclusion principle does not apply. Because then they wouldn't actually be in the same state.
Yeah, and therefore the identical property is crucial for this, right?
Yeah, I think so.
Thanks. Okay, so, and further, he says the quantum Hamiltonian approach, which provides us with Schrödinger equation for the evolution of quantum state vector, still applies when there are many particles, possibly interacting, spinning, etc., just as well as it did with a single particle without a spin. Okay, and he says that all we need is a suitable Hamiltonian to incorporate all those features. And we do not have a separate wave function for each particle. Instead, we have one state vector which describes the entire system. Okay, so he says basically that for many particles, we will need updated wave function, which will kind of tell us about the holistic nature of a system, basically. Yeah, and in a position space, a wave function will be a function on the configuration space of the system of particles, and it could also depend upon some discrete parameters to label the spin states. For example, if we use a two-spinor description to describe a spinning particle, the discrete parameters would be labeling the different individual components. Okay, so, and Schrödinger equation will tell us how that wave function evolves in time, so the wave function will need to depend upon the time variable also here. Okay, and he says here that we will have like one time dimension for every particle. Yeah, and that kind of this is a curious feature of non-relativistic quantum mechanics, and if we think about relativity, then we will need like a more complete picture for the relativistic theory here. But as for now, we should think that there is only one time for all of the particles. Okay, and we need more. Yeah, we will need more times basically in relativity case. So the same way we have like different, basically different positions for different particles. The same way we will have like relative times there. Like mixture of space and time in relativistic case. Okay. And indeed, this viewpoint has been adopted from time to time by various authors, going back to the late 1920s, but it doesn't seem to have been developed into a full-blown relativistic theory. And a basic difficulty with allowing each particle its own separate time is that then each particle seems to go on its merry way off into a separate time dimension, so further ingredients would be needed to get us back to reality. Okay, so basically in 1920s there was some kind of trying to build a nice relativistic picture, but there were some difficulties and they were resolved later. And we will see in chapter 26 that we need to introduce path integral approach for that. based on the relativistic Lagrangian, rather the Hamiltonian formalism. And it will help us to solve that problem. However, as we shall see later, serious new problems come in. Yeah, and we shall be seeing shortly that the ordinary Schrödinger equation itself is not immune from the difficulties of getting back to reality. Okay, and in his opinion, this simple space-time asymmetry of the Schrödinger approach hides something deep that is still missing from our quantum picture. But for now, we will ignore those issues or these issues and present things merely from the standpoint of the non-relativistic quantum theory, where the notion of the universal external time is just kind of set up. So we will talk about relativity case later. Yeah, so how then are we to treat many particle systems according to the standard non-relativistic Schrödinger picture? In chapter 21, we saw a Hamiltonian in which all momentum variables must appear for all of the particles in the system, and each of those momentas were replaced in the quantization prescription of the should be replaced using the quantization procedure, using those differential operators we've seen already. Okay, and all these operators have to act on something. Yeah, and that something is the one holistic wave function for the whole system. And this wave function must be indeed a function of the different position coordinates of all the separate particles. Yeah, so basically for the many particle system, you'll have one Hamiltonian and one wave function, and all of the momentas as differential operators included inside somehow. So basically that first subchapter was like a sketch for the further inquiry, basically. And all it was saying is kind of concluded in that last paragraph, actually. And it also included a bit of the relativistic discussions about time and path integrals, basically. So it seems that that's actually it. Okay, so maybe you had some questions about the first subchapter here. Okay, so let's continue. Let's continue then. So the next subchapter talks about the hugeness of many particle state space. And last requirement was about the dependence, like, of the wave function on all of the different positions, coordinates of all separate particles. And here he says that if it were the case that each particle had its own separate wave function, then for n scalar particles, non-spinning, we should have n different complex functions of position. And also this is a bit of a stretch of our visual imaginations for n little particles. It is something that we can perhaps just about cope with. And for visualization purposes, we could have a picture not so unlike that of a field in space with n different components. Okay. And perhaps we should consider these as 2n components if we are talking about real components, because wave functions are complex. Okay. And for example, electromagnetic field has 6 real components after all. That is 6 functions of 3 variables, analogous to 3 complex scalar wave functions. Okay, and a field of electric and magnetic vectors is not such a terrible strain on the imagination. Yeah, okay, so in electromagnetism we have like electric and magnetic fields, and they occupy like 3 dimensions, so we have 6 functions, 3 per each field, and all of those depend on the positions x, y, and z. That's why we have 3 variables here. Okay, so he says that that field example is kind of a simple one. Like if we had like 3 basically independent particles and one wave function per particle. Yeah, and how we can estimate the field freedom in that case. And you can recall that in chapter 16 we had those infinity expressions to talk about sizes. So, but basically they're just talking about like cardinal numbers. Basically it's about cardinality of the sets. And those powers, they basically are about the functions. So if you have a power, it's like function from one space to another one. And let's take a look what he means here by A and B, for example. So he talks like, how are we to count the freedom in complex scalar field, such as the wave function for a scalar particle in 3 space? What is the number of different possible such fields? And recall that according to the notation of the chapter 16, this sign denotes the freedom available to a freely chosen smooth field with A real components in a space of B real dimensions. So let's think about this a bit. If we have A real components, those are functions from like real numbers. Yeah, and we have A functions. A functions. Yeah, to the field of the real numbers. Okay, yeah, and that's it. So basically, it's the same thing you can think about, like combinatorial stuff. Like if you have, I don't know, like a set with 2 elements inside, and for example set with 3 elements inside, then how much combinations or like basically functions you can build up between those sets. And that will be like those 2 things, like 1 and 2, have 3 different options here to become, and therefore the space of functions will be like 3 to power 2 here. And in the same way, if you replace 3 here with the real numbers, like real numbers line here, you'll obtain like infinity squared, right? And if you increase like and add here more dimensions, like he was doing here in a space of B real dimensions, A real components in a space of B real dimensions. Probably every component will be also a function from B. So like his approach is that like every component from the A set, like AI for example, will depend on like x1 xb number of dimensions here, and it will be also function to R, and therefore we will have that infinity to power B thing, and we will have how much of those components? A. Therefore we will have A multiplied by that, and a field, the global field dependent on all of that functions, will have like infinity many of those like combinations. Okay, so basically that's that scene is kind of just describing a number of functions, total A functions, or like field freedom depending on A components in a B-dimensional space, basically. Okay, so in ordinary 3 space, given B equals 3, and for 2 components there, we will have something like that, like infinity to infinity to power 3 here. Okay, and what we'll have later here, in the case of the function, okay, let's skip the ending of that paragraph. Kind of that doesn't matter currently. Yeah, and afterwards he talks about the electromagnetic fields and how much of the freedom those has, or those have. Okay, and he says that a free Maxwell field with no sources, like charges to worry about, will have 6 real components in ordinary 3 space. So we take the field just at some fixed moment of time and ignore the Maxwell equations. So we will get the freedom of that cardinality here, like infinity to power of 6 infinities to the power of 3. But the Maxwell equations imply that 2 constraints must hold on any initial data tree space, namely the vanishing of the divergence of the electric and magnetic field vectors, and this reduces the effective number of free components on the initial data 3 surface by 2. So the freedom is actually, so basically just eliminates 2 components for the fields because of the dependence. So you will have 4 instead of 6 here. And now we can consider the quantum mechanical description of n-scalar particles. And if the description were just n different wave functions, then the freedom would be like this one. So we just will have n here, just multiplied by the infinity. Since that is the freedom in choosing n complex numbers, and 2 because we have like 2 real parameters here, per point in 3 space. So 2n and 3 for the dimension of space here. But in the case of an actual quantum wave function describing n-scalar particles, we have one complex function of 3n real variables. And this is like a complex scalar field in a space of 3n dimensions. So the freedom now will be like this, and the n will go to the power at the up of that equation or formula. So basically n going to the upper power here just means that we have a functional dependency. So our functions will depend on all of the coordinates instead of just having n functions of like 3 coordinates in space. And that space will be stupendously larger because of the more powerful powers, basically. And it's probably not so easy to appreciate the enormity of this increase. So Penrose here talks about the toy example. He just takes a toy universe in which we have only 10 points. We can label those 10 points by the 10 numbers, like from 0 to 9. And he says that the wave function of a scalar particle in this universe would just consist of the complex number at each one of those of these 10 points. So 10 complex numbers, z0, z1, z2, and z9. And the space of all these wave functions could be the 10 complex dimensional Hilbert space H10. And that's it. And if we normalize, and that H basically is like C. So basically it's like C10 here. And if we normalize the wave function so that the sum of the squares of the moduli of those z's is unity, then and then, for example, these 6 modulus squared would represent the probability of a position measurement, finding the particle at 6, and so on. Okay, and this discrete model is not really such an absurdity. In actual physical situations, one might have what is in effect a sequence of 10 boxes with an electron that might be in one of those. And experimenters can construct things of this nature called quantum dots. And they have relevance to the theoretical possibility of constructing quantum computers. So back to the example, suppose that there are now 2 particles in our universe. It is better that they are not both the same kind of a particle, for reasons that I shall be coming to later. So let us call those particle A and particle B. And each of the 2 particles could be in 10 different alternative places, because we have like that basic 10-point universe there. So there are 100 different possible placings for those, for the pair of particles. And we now need like 100 different complex numbers to define the wave function. One complex number being assigned to each pair of placings. So like for a combined system, if we have had like 2 wave functions independently, and having like 10 numbers, 10 possible numbers to describe one, and 10 possible numbers to describe 2. So overall space is like H100. And if we normalize those, then the same thing will be with those modulus of these there. Okay, and and that probability will talk about the system in terms that A particle will be at 0.3 and B particle will be at 0.8 with this probability. And we are now dealing with H100. And if we had 3 different particles, then we will have space, in this case H1000, and etc, etc. So for 4 different particles we'll have 10 to power of 4, like 10,000 here, whereas for 4 individual particles, for 4 individual wave functions, sorry, probably I forgot to tell. I confused you a bit. Sorry. So those like powers of 100, 1000, and 10,000, those are connected with the like real world wave functions, like wave functions depending on all of the positions of particles. But for only like in terms, if you have like three wave functions for the particle in 10-point universe, the overall space will be just n multiplied by 10, so only H30. But in the quantum world we have 1000, and the same way for like 4 independent wave functions, we would have like H40 here, but in reality we have like H10,000. So it's kind of like a big boom, enormous space actually of the possible variants for the particles to be in for the like complex or n-particle systems. So if you revert back to the infinity notation, we can see that that infinity to power of 3 refers to the number of points in Euclidean 3 space, and that number is now replaced by 10 instead, because we have only 10 points in our toy universe, and the actual number of points in our toy universe, and therefore that thing will become only like infinity to power A10 to power n, which denotes the number of points in the A multiplied by 10 to power n real dimensional space. So that's just the function from this much of components to the R, to the real numbers. And thus, instead of having this thing for the freedom in an n-particle scalar wave function in E3, we would have two, like for two particles, right, multiplied by the 10 to the power n here for the freedom in an n-particle wave function for our toy universe. And the complex Hilbert space will be described by the h to the power 10 to the power n. Instead of the n not being in the power here in the exponent and being just a multiple here for the power of 10. And therefore you can see that like this space is kind of enormously bigger than this one. So the question is, what is hidden there in such a big, enormous spaces for wave functions for a complex systems, like with more particles in it than one? And the answer will be given later in terms that basically it's quantum entanglement there, and we will talk about this in the next subsection. And maybe you have questions about the previous one, because I was a little bit maybe back somewhere.
So I think the distinction that he's making between the like individual particle wave functions and then like the full wave function for the whole space, it would be the difference between like a direct sum and a tensor product. Or
not even the direct sum, but also like Cartesian product also, right? Or am I wrong here? Let me think.
Which one here would be the Cartesian product?
Maybe I am wrong. Yeah, because like if we have like two spaces like P plus Q, the direct sum case you've been talking about, and we have like n dimensions and P dimensions here, then we will have just n plus m dimensions here, right? But if we have Cartesian product of P and Q with the same dimensions, we will have n multiplied by m.
Right. I think we're calling it different names, but we're talking about the same thing. I just called the Cartesian product the tensor product.
Yeah, but like probably I should use different. Sorry, this thing here. So this is Cartesian product and tensor product, but maybe that's the same. Yeah. Okay. I think that will be the same as Cartesian product, right? Because for okay, true. So this is a tensor product and this is direct sum. Okay.
Well, yeah, that gives us a huge difference in the dimensionality. So I think the significance of using the tensor product here is because this includes the entangled systems as well. Whereas the direct sum would just be like they're all individual independent systems. And then the tensor product here gives you all of the entangled or interacting states as well.
Yeah, but like what I've been thinking about is something like this. So if you have like, for example, two particles and only like two wave functions in space, so I will just, for example, say like x, y, z here, right? Psi1 and psi2. So in the case if they are independent, then and we have scalar particles, right? So we will just use like complex numbers for those wave functions. Then this function will be like a function from R3 to C, and this one from R3 to C. And therefore, like the overall wave function composed from those two, like depending on psi1 and psi2, will be, yeah, basically the function from the direct sum, right? Or no? Yeah, probably right. Probably right, because maybe we will need like a pair of points.
Well, so I think that the overall wave function would be from C cross C to C.
Ah, yeah, like combinator, you mean?
Yeah.
Yeah, I understand what you want to do here. So like just instead of R3 here, we need to put like a functions of actually like those signatures inside of the arguments here. So we need to give the input like two positions for a particles. We will obtain like two numbers. And by having those two numbers, we can kind of combine them using the higher order combinator here and output C here. Yeah, but that seems kind of, so like direct sum here guarantees kind of the independence, right, of those particles.
Yeah, so that would be like non-entangled. So this would just be like a subspace of the entangled, or it would be a subspace of the tensor product space would give us this direct sum. Well, it's okay.
Yeah, it's okay. I just been trying to answer the question. The question, like I've been thinking about the functional dependencies and non-functional. So, for example, if you have this dependency, like from P to Q, then the corresponding algebraical expression is or will be m to power n. And I've thought that like for the entanglement and for n-particle quantum systems, we like the crucial property of those lies somewhere here, like in the functional dependence. That's why I wasn't really comfortable with like the previous comments, you know, because like intuitively I was thinking more about this thing rather than tensor product. But actually, like tensor products are really connected with the functions. Yeah, because we can, for example, like carry those. But Okay, probably I'm just going into some other direction currently, so I will think more about this later, or maybe I will understand something while talking more about the next subchapter.
Yeah, and I think that the important conclusions that we got here is that the direct sum space is like independent systems, and then the tensor product space is for like the entangled wave functions as well.
Yeah, and actually that's exactly the uh, um, material of the ending of the next subchapter here about tensors. So, okay, we will come back to this question only a bit later. So let's start discussing the next subsection, and this section is about quantum entanglement and Bell inequalities. So basically, like, what is all this extra information doing? And Penrose says it is expressing what are known as the entanglement relations between the particles. And how we can understand these entanglements between particles, a notion first made explicit by Schrödinger, are what lead to extremely puzzling but actually absurd phenomena known Einstein-Podolsky-Rosen or EPR effects, and they are rather subtle features of the quantum world. But like the question here, why they are like so hidden, like they are quite hard to demonstrate experimentally, and and it seems like interesting why they are so hidden from the view when for the many particle systems almost the entire information in the wave function is concerned with such matters. Okay, and this is a puzzle what we will come back shortly in the subchapter number 6 here. And in Penrose's opinion, this puzzle is trying to tell us something about what kind of new directions our present-day quantum formalism ought to be moving in. But be that as it may, it is certainly telling us something about the potential power of quantum computing, which aims to exploit the enormous information resources that lie hidden in those entangled relations. So basically, quantum computing is relying on the entanglement power and the enormous dimensionality of the n-particle system space. So what is quantum entanglement? What are EPR effects? And to consider this, we should address the David Bohm 1951 model for these. That's kind of the simplest EPR situation. And he says here that we will talk about finite dimensional situations here, and we will concentrate on states of spin. So, and Bohm in the Bohm's experiment, we have like a pair of spin 1/2 particles, let's say particle PL and particle PR, which start together in a combined spin 0 state, and then travel away from each other to the left and to the right to respective L and R detectors situated at a great distance apart. And let us suppose that each of the detectors is capable of measuring the spin of approaching particle in some direction that is only decided upon when the particles are well separated from each other, like non-interacting already. And the problem is to see whether it is possible to reproduce the expectations of quantum mechanics using some model in which the particles are regarded as unconnected, independent, classical-like entities. And here is the picture of that setup, like the particle source, one particle flying here, other one to the right, and we have like Stern-Gerlach detectors here to measure spins. in different orientations in space. One to the right, one to the left. Okay, yeah, and it turns out, because of a remarkable theorem due to the John Bell, it is not possible to reproduce the predictions of quantum theory in this way. So Bell derived inequalities relating the joint probabilities of the results of two physically separated measurements that are violated by expectations of quantum. Alex disconnected for a minute. Okay, are violated by the expectations of quantum mechanics, yet which are necessarily satisfied by any model in which the two particles behave as independent entities after they have become physically separated. Thus, Bell inequality violation demonstrates the presence of essentially quantum theoretic effects which cannot be explained by any model according to which the particles are treated as unconnected and independent actual things. Give me a moment, I need to pour some water. Just have a sore throat from talking. Okay, back to the book. So basically we have that setup, and we know that there is some kind of the inequality developed by the Bell, and we know that we can check experimentally, or at least try to check if those inequalities like hold or not, and they're actually violated by the expectations of the quantum mechanics. So if those are violated, then the real nature of the reality is like quantum-like, and if they could be held somehow, then we can kind of believe that we have like no entanglement or like no connectedness between those two particles. Okay, and there are many striking particular examples, and some of these refer to the Bell inequalities without probabilities. They're particularly remarkable in that they just involve yes or no issues, and we do not need to worry about probabilities, or rather, we worry only about the extreme definite cases of probabilities like never and always, 0 and 1. And we will talk later about two examples. The first one example developed by Henry Stepp in 1971 and is a direct example of the original Bohm version of EPR as referred to above. And the second one is due to the Lucien Hardy, developed in 1992. And it's almost a version without probabilities, but it has a slight extra twist to it. So we will talk in the next subsections about those. And basically in this subsection, Penrose just kind of introduced the EPR and talked a little bit about quantum computing, talked about Bohm setup, talked about Bell's inequalities, but only in like a really superficial way. So he only scratched the surface here. And talked that we will have like 2 examples in the later subchapters. Okay, and for the end here he talks about math a bit, about the tensor products. So he says that before we will give you the detail, we need to discuss more of the direct notation. And suppose that we have a quantum system that consists of 2 parts, psi and phi, which can be taken to be independent of each other. Then if we wish to consider the quantum state that consists of both of them together, we write this as psi phi, something like this. Actually, like I also know that we, for example, can write this something like that. So it's also okay. Like not write too much brackets. Yeah, and this is still a single state, and it would be legitimate to write an equation such as like he equals to those 2 states multiplied, which expresses this fact. Yeah, and like in mathematics or in some papers you can also see notation like this, like psi 5 is that X or tensor product stated directly. So Penrose just do not include that here. Okay, and the type of product that is being employed here is what is called the tensor product by the algebraists, and it satisfies the next laws here. So you can multiply it on the left, and it is the same as to multiply it whole, or on the right part. You can also, it's linear on the left, and it's also linear to the right. Yeah, and the operation of tensor product is commonly denoted by that x. Yeah, and I have said about this already. And in any case, it is handy to use the x symbol in connection with the Hilbert spaces to which such products belong. And thus, if psi belongs to HP and phi belongs to HQ, then the tensor product belongs to the HP tensored with HQ. And the dimension of the tensor product will be equal actually to the product of the dimensions instead of summing those. And that was exactly the fact Joe was talking about previously. So we will have like the overall space H of the dimension P multiplied by Q here. Yeah. And Penrose allowing here for P or Q to be both or any of those to be infinity, in which case we take the product to be also infinity. Only a very small part of the tensor product space consists of elements which are just pure states, like which could be separated basically in 2 independent particles. So, for example, we will see soon the example of the state which cannot be separated. I mean, we will prove that. But basically it will be like some algebraic combination of those pure states, which kind of form the basis of the tensor product space.
While we're here, I wanted to point out how I've heard like my professors say this sort of thing. So like that in the second to last paragraph here, the last thing that's written where they have the psi tensor product with phi. The way that I've heard like professors say this is they say ket psi tensor ket phi. It's not an important mathematical distinction, but just in terms of like reading it aloud or like in your head sort of thing, it's ket psi tensor ket phi.
Thanks.
Also, while we're at it, I think it's pronounced linear.
Linear. Yeah, it's my how to say that.
Dialect.
I'm kind of used to making that mistake. Linear. Okay. Okay, so what we have here, we have a ket of psi, which belongs to HP here, and phi, which belongs to HQ here. And these are the unentangled states. And a general element of the tensor product would be a linear combination of these unentangled states. Linear combination of these unentangled states. Yeah, that's true. Okay. And possibly involving an infinite sum of or integral if both P and Q are infinite. So basically it's all about the basis for those HP and HQ spaces. So if you have like EI basis here, for example, and in HQ we have some F, I don't know, J, for example, basis, right? Then we can form the basis for the tensor product by tensoring all of those basis vectors, like EI with Fj, and therefore we are obtaining automatically P by Q new basis vectors, right? So yeah, and here at the end of this paragraph, Penrose talks about splitting of the bigger Hilbert spaces. So if you have some kind of quantum system and Hilbert space h to the power pq here, then like the very notion of the entanglement will depend upon the particular splitting of the entire space into something like HP multiplied tensorially with HQ here. But no one such splitting of a general Hilbert space is to be preferred over any other. So we could have like different splittings here with the fixed dimensions. And algebraically, there will always be many ways to express Hn as a tensor product whenever n is a composite number. And in situations where one is interested in the entanglement notion, the particular splitting of physical interest is something reasonably obvious. So probably we will not worry about that, but we should consider that splitting is not unique anyway. Yeah, and most notably when there are individual particles separated by a large distance, which is what EPR is all about. Okay. Yeah, and at the next paragraph here, Penrose just mentions the abstract index formalism, and we have seen that in the previous chapters, and it was introduced in chapter 12. And for example, cat vector could be written using a vector notation with the upper index here, and the vector bra here could be written with the lower and also like with the conjugation dash at the top here. Abstract index and the full bracket could be written as the contraction of those two, like one form and vector basically. And the sandwich operator could be also written in the same way we were writing the matrices in the tensor notation. And the tensor product now could also then be written as just two vectors glued together basically. Yeah, and unentangled states always split in this way, but a general probably entangled state would simply be an entity of the form phi of alpha and beta here with two indices. And we shall be seeing as a particular use for this kind of notation later in this chapter. I saw that Yuri for some reason disconnected from the stream. So let's talk about this subchapter. Maybe you have some questions or some commentaries to add for the subsections number 3.
I just posted a quick little fun fact in the chat room. This might help people get like a more mathematical grip on like the tensor product. So the tensor product is a bit like the outer product of a column and a row.
Mm-hmm.
And you can see in the picture I posted, the first matrix on the upper left can be decomposed into like a outer product of a column and a row. But the matrix at the bottom, you can't do it. It ends up being impossible. So that's sort of like why tensor product of two states is more complicated than the individual states. You can't always split up a matrix into a row and a column.
Mm-hmm. Yeah.
So I don't know, maybe that's obvious to people, but that kind of helps me a little bit.
Yeah, thanks. That's actually a really good example because it kind of simply shows the entanglement actually, yeah. And we will see something similar in the next subchapter when I will try to show you the basic like unseparability of the Bell state. Yeah, thanks, Chris.
And I had one other kind of question or comment. Because in quantum mechanics, you deal with like bras and kets a lot, right?
Mm-hmm.
And in relativity, I'm used to calling those vectors and covectors. So vectors are the kets and covectors are the bras.
Mm-hmm.
And to change between them, that's what like raising and lowering indices is with like the metric. I don't know if you guys remember that.
Mm-hmm.
Yeah.
In quantum, it seems like to change from one to the other, you just take the complex conjugate of the components. I was wondering, like, is there like a metric involved there, or like I don't know. I was wondering what the connection is, if there's like a connection.
So
yeah, so I think it's not just the. Oh, sorry, Slava.
Yeah, talk, Joe, talk.
I think it's not just the complex conjugate. I think it's the Hermitian conjugate, where you would have a similar distinction between like vectors and covectors, but I think that the metric here would just be the identity. I don't think that there's anything special.
Okay, I see. So I guess that all the states are orthogonal to each other, which is why the metric could be thought of as the identity. So you don't need to worry about it, I guess.
Right. So that bra of psi is the conjugate transpose of psi.
Yeah, right. I guess I misspoke. I was thinking of the components only, which are just the complex numbers, and those would be just the complex conjugate. But I guess for like if it was an operator, then you'd need to take the full Hermitian conjugate.
Right.
Yeah, but like anyway, we will always have like orthogonal bases for our Hilbert space in like traditional quantum mechanics. So like no matrix will be introduced, I think.
Okay.
Yuri, maybe you have some questions. Or maybe you missed something because you disconnected for a moment.
I was dropped off, so I lost Chris' example of the entanglement.
Yeah,
I guess.
Chris's example, probably I will just, for the video's sake, I will include it here. So basically, for example, if you have matrix like this, like 4, 400, and for example 8 and 800, you can see that those two rows, they are kind of collinear, and two columns, they are also collinear. So you can like separate those into a column like 4 and 8 here, and into a row like 1 and 100. And using those, you can just multiply each of those number to obtain the matrix, right? At the corresponding position. Like 100 by 8 will be 800. But if you will use non-collinear matrices, like for example 100 or 1800 here, for example, you will not be able to separate that matrix into some kind of the like numbers here and numbers here in like row column decomposition. So it will be impossible to decompose. And this example basically shows you that tensor product, this space of matrices, is much larger than a direct sum, which represents like a row and a column independently.
Interesting. Yeah, I've never thought about like this before. Yeah.
Oof. Okay, so let's talk about the last subsection for today, number 4, and I think we will think more about that, or maybe about some examples from it later. Okay, so now we kind of come into the real deal here, because Penrose, from the beginning of this subsection, he introduces the actually entangled state described here, or with that like omega letter, right? And he says that basically because of the conservation of the angular momentum, when particle or like will divide, for example, I don't remember what kind of scene will kind of be split into two spin 1/2 particles, like pion or muon in 2 photons or something. But basically we have like one particle, it splits into 2, and the original particle has spin 0, and one particle will have like spin 1/2, and other one will have like minus 1/2 or something. Yeah, so anyway, that's kind of two situations. So if we will use a basis to describe a spin, like up-down basis here, then basically we have two situations. Like either one particle will be at the up state and the other one will be down because of the angular momentum conservation. All another particle, or like first particle will be down and the second particle will be up. And we have like basically algebraical combination here of those states. It seems to me that it is not really important if we will have like plus or minus here. I think that both of those states will be Bell states and will be entangled, but Penrose here uses the minus sign for some reason. And if you want it to be in like a real way, you should normalize these, and to normalize you need to include 1 over square root of 2 factor here. So the amplitudes, instead of being 1 and minus 1, will be normalized, and you will have correct probabilities from those. And basically probabilities will be 1/2 and 1/2, right? Because like I can think of this like a symmetry argument here. So basically we have nicely balanced system, symmetrical one. So like those two situations will have like equal probabilities. Yeah, and later Penrose says that sometimes in some literature people write like up left and down right. So they also use letters there to explicitly state to which particle state belongs. But actually tensor product is not commutative one, and therefore it's kind of obvious that the thin on the left is the particle on the left, and the thin on the right is the particle on the right. And actually, personally for me, I don't like those arrows, and I kind of don't like y and nose notations here. So I'm kind of more adjusted to the quantum computation notation when you have like 0 and 1 states, like bits basically. And for Bell state, you'll have like 0, 1 state, and it's kind of native. And for some reason, maybe because of my software engineering background, it's easier for me to look at those 0 and 1s than arrows, but not sure about that. So anyway, yeah, and here Penrose said that this is a clear example of an entangled state, since it cannot be separated basically, or rewritten in the form of two independent alpha and beta states, with alpha localized at the left and beta localized at the right. And he gives us as an exercise to prove that. And actually it's pretty easy to be done. Let me take a look. I had some pieces of paper I've been working on. Maybe it's not really presentable, but anyway, I will try to show you those. Sorry for my bad writing here, but anyway, so if you have, I've been marking and using those like 0, 1 and 1, 0 notation. So basically it's the same like the up and down arrow or arrows, and I have the Bell state on the left here. And I assumed for a moment, so let's assume that we can separate that state into two independent one-dimensional states for each particle on the left and on the right. So they will be described by the 0 and 1 one-dimensional cats here. And they will have different probabilities, like alpha, beta for the first particle for those two measurement results, 0 and 1, and C and D amplitudes for the second particle. And if you open up the tensor product, you will just have like alpha C 0, 0 plus beta C 1, 0 plus alpha D 0, 1 plus beta D 1, 1. And now you can see that you have like 0, 0, 1, 0, 0, 1 vector cat and 1, 1 cat here. And you can just kind of make coefficients on the left hand side and on the right hand the same. So you can say that alpha C equals to 0 because coefficient on the left hand side near 0, 0 is 0, and beta C is minus 1. So that's exactly like we will have 4 equations and a system of 4 equations here basically. And you can see that those equations actually are not are not like doesn't have a solution. Why? An answer is really easy, because we have like beta D equals 0, and therefore either beta or either D equals 0. And from the second equation we have like alpha C equals 0, and therefore alpha either like alpha equals 0 or C equals 0. But we also have those two equations. It's alpha here. So basically beta C equals minus 1 and alpha D equals 1. And from those two on the right here, we can see that if you take any of those, any combination, that will imply that those two equations will be zeroed. And they are not 0. And therefore, because they are not 0, we just have like incompatible system of the equations, and we have no solution. So, and that's basically it. And actually that's the same thing Chris was demonstrating with the matrices, rows and columns, with like a more simpler example. But the overall procedure is the same. So the row and column are like two columns here basically. They are like one dimensional states for particles. And matrix is the state for that tensor product thing. And we can say that the matrix for that one is like 0, 0 for 0, 0 and 1, 1 state. And for 0, 1 it's 1. And for 1, 0 minus 1. So it's like a matrix. So we can like kind of reformulate in the real close form to the Chris used in his example. So that's the actually proof why we cannot separate the Bell states into two independent particle states, and therefore that's called entanglement, because we cannot. Oh, and Chris sent the his version of the proof to the chat. So let's see it.
I don't have too much to say. It's more or less the same thing that you said.
Yeah. So basically, you form the same matrix I've written on the paper. That one with zeros on the diagonal and minus 1, 1 on the complementary diagonal. Yeah, and basically we cannot separate that matrix into row and column because you will obtain the same system actually I've written here below.
And this is a great example because it's related to what we were looking at last week with the Clebsch-Gordon coefficient tables. You'll see that the ones that can be separated, one of those coefficients is 0, but for the ones that can't be separated, all of the coefficients are non-zero. So like in this case, we're talking about like a total spin 1 state composed of 2 spin half particles, and in that case, none of the coefficients are non-zero. Or I'm sorry, all of the coefficients are non-zero. None of them are 0.
Yeah, so you was talking about the matrices we have seen in the paper you've been showing us on the previous call, right? With those D numbers or something.
Yeah, that's right. So that table again, it'll go from like a 2-particle state where each particle has like spin half or spin 1 or whatever, and it'll go into a like total spin state. Mm-hmm. And so what I'm talking about is whether those coefficients are 0 or non-zero. And I think in the case where all of the coefficients are non-zero, it can't be separated out.
But like I just been thinking that Chris has an example, right, where all coefficients are non-zero, but we can separate because they are collinear. So maybe if they are not collinear, like linearly independent in the rows and columns.
I see. Yeah. Let me think about it. I'll post something in the chat in a few.
Okay.
I think I think Slava has it right. Like basically, in order to do this, and this is true for like 3x3, 4x4, 5x5, you need all the columns to be multiples of each other, and the determinant of the matrix ends up being 0 because of that. So you can't like using this like column times a row method, you always end up with a determinant 0 matrix. So it ends up being a really sort of, I guess, simple matrix, whereas the more complicated matrices that have a non-zero determinant, you need like linear combinations of several different tensor products, if that makes sense.
Mm-hmm.
Yeah, I think that's right. And I think that is actually what I was trying to demonstrate with the Clebsch-Gordon table, but I'm not doing it off the top of my head yet.
Okay, so now let's go to the interesting results. So if you consider the Bell state from the previous example, that one with like up, down, and minus, down, up things, the omega, then if I, being at the left detector, perform the measurement of the spin of the left-hand particle in the up direction, and for example, if I get no, then it will automatically project to the minus down up state, because that's the only state we can get on the left detector the result down. And this will mean for example, Joe being at the detector on the right, that he will receive the up state particle at his detector. So basically, by measuring it on the left, we kind of automatically can say what will happen at the detector on the right. Penrose also makes a small remark here about the entanglements that accept that standard U evolution, basically Schrödinger equation, would tell us that PL, like our particle on the left, is now likely to be entangled with my own measuring apparatus L. And basically, like, there is such interpretation, I think, or something. So I also read about that in the Leonard Zaskin book about quantum mechanics, that if you measure a particle, for example, then your measurement apparatus and you observing the result are kind of automatically entangled and sucked up into the wave function of the whole system. Yeah, but anyway, that's kind of just a remark here, I think, maybe important one, but what is more important is the connectivity or like causality of measuring one, like something at one place and implying the result of measuring something, another one seemingly disconnected from it at the other place. Yeah, and what is curious here that it's also doesn't depend on the orientation of your detector. So basically, there is nothing special about the up-down choice in all of these. And for whatever direction we will choose to measure, for example, that like left down arrow, then if my colleague chooses the same direction, the result will be opposite. And this should be clear from the rotational invariance of the spin zero. It is not clear for me, actually. Maybe someone can explain it geometrically, but Penrose says that anyway, we can think about another Bell states in another bases, like those ones. So we just have another basis, like bottom left arrow and top right arrow, and we kind of describe those particles using the new basis. And for that new state in the new basis, we can check that actually nothing will change for that new basis if we move to it from the up-down basis. And that actually what could be done pretty easily. You just need to take a representation of the top-down or bottom left arrow in terms of up and down, and also its orthogonal right top arrow, or also in terms of right and down. You can see that it is basically conjugated transposed thing here, so to be orthogonal. So if you kind of multiply that by that, you will have 0. Yeah, and you just need to substitute those two things inside here, and if you substitute and open up everything, you will obtain something really interesting. So I will just briefly show you the results. So if you have the new basis here, and we also know that probabilities are described as the squares of the modulus of A and B's here, actually. And we know that some of those squared modulus are equal to 1. Yeah, and basically I normalized here the state, like added 1 over square root 2 here, just for simplicity. But anyway, here I'm not using it, so I just substituted everything, like those two formulas, into this one, obtained like 8 parts for the cats, tensored cats here, and a lot of things just kind of eliminated each other, and everything I've kind of what is left here is the things like that, like B conjugated, A plus A conjugated. But we know that B conjugated is just like modulus B squared. So actually what we have is like some kind of number C, and that C number is actually equal to the A squared plus B squared, and we know that those are probabilities, so it should be equal to 1, and therefore we will have the same state actually. So independently of the basis, the state will be the same and the probabilities will be the same for any orientation in space or along which we will measure the spin. So it doesn't matter. Any basis is good enough, and for any basis we will have different, same probabilities, like 1/2, 1/2 for those states. Yes, and that's interesting because it's kind of not so trivial, because probably, I don't know, my intuition was telling me that those will be different or something. I don't know why. Maybe I was thinking that like if particle to the left will go and have like spin, something like that, like along that line, then if you will measure it by up here, you'll have like a different probability or something. But it seems that it doesn't matter. So we will always have 1/2 of getting our spin here up and 1/2 probability of getting our spin down here. And that's kind of not really intuitive to me without like previous algebraic expressions. But yeah, anyway, that's like it should follow from the how it's said, basically Galilean inequality, like anisotropy of space, right? Because every direction is equal, and for spin every direction is also equal, as we have seen in the previous section. So basically that's kind of follows directly from it, and also algebraically. But I believe in algebra here more. It's kind of more I don't know, things which I can appreciate more here. Okay, maybe you have something to say about this, or something to add to that example.
Well, I wanted to point out the example that I gave with the Clebsch-Gordon coefficients, and I was wondering if we could try to make sense of it. So I posted it in the beta chat.
Mm-hmm.
And so the idea here is that like the columns are the like total spin states, where like 1, 0 represents the total spin state 1 with z component of spin 0. And you can write this as like a combination of the rows here. So in the LaTeX that I put after that, I actually like expanded out just that one term in the table. So I'm wondering if we could relate this to the idea of like not being able to decompose an outer product, or I'm sorry, not being able to decompose a tensor product in the way that we can just a standard outer product. Chris, do you see a relation here between what we're talking about, or am I talking nonsense here?
Sorry, I was muted. So I need to go back and review the Clebsch-Gordon coefficients, because I'm having a bit of trouble reading this table. I don't think I ever fully understood it. So you have like the J, which is like the total spin state, and then the M, which is like the individual spin.
Yeah, M
Sorry,
is the Z component.
Right, okay.
So for like spin half, M could be plus or minus 1/2.
Okay, right. And how am I meant to read this Clebsch-Gordon image here? Could you explain that again?
Yeah, so I'll write down this same kind of LaTeX for the top element. Yeah, just one sec.
So here we have a system of two particles with spin 1/2 and 1/2, right?
Right. Yeah, maybe it's best for me to just like highlight the table. So one sec. Here's a picture from the table of actually like how to read it. So let's just look at the first row and the first column here. So M1 and M2 are the Z components of the individual particles. So like M1 could be plus or minus 1/2. M2 could be plus or minus 1/2.
Mm-hmm.
And in this case, J would be either 1 or 0. And M here is plus or minus 1 or 0.
Mm-hmm.
So that's sort of how to read this table, is that the columns of the table tell you the total spin states, and the rows of the table tell you like how to decompose those total spin states.
So, for example, the only way to get a +1 capital M is to have +1/2 and +1/2 for the individuals. And then the only way to get a -1 for the capital M is to have -1/2, -1/2 for
Yeah.
both.
Yeah.
And then in the middle, I guess it's more interesting because it shows the different ways you can get 0.
Yeah, that's exactly right. So the examples that you just gave are the first coefficient and the last coefficient, which are both 1 because they need to add directly, as you mentioned.
And so what I'm confused about is the stuff in blue. What do those numbers mean? Are those the actual Clebsch-Gordon coefficients?
Yes. Yeah. So I wrote down the first coefficients in this z component 0 part of the table. So if you look at the LaTeX that just follows, I have the j equals 1, m equals 0. And so each of the coefficients on there, it says 1/2, but it's understood, like it mentions it at the top of the table. This is why I put the link there. It mentions it at the top of the table. All of these coefficients have a square root on them. So when both of the coefficients are 1/2, then that means really 1 over √2.
Mm-hmm.
So yes, the stuff that's like in the middle where it's kind of like filled in, that's all the actual Clebsch-Gordon coefficients.
Yeah, so those matrices are like things in gray or blue. It depends on your monitor. Things on my monitor, those are gray. But anyway, those are just like amplitudes.
Right.
And in contrast to the Croesus example, here we have like a bit other dependency on M and J numbers, basically. So for example, like a row on the left, or like rows, right? They are connected only to the second entry of the column, and they are kind of sums of those.
Yeah, that's exactly right. So where J1, oh, and I noticed I made an error in my LaTeX. So where J1 and J2 are is the 1/2 cross 1/2 that we see on like the top left side of the picture.
Mm-hmm.
So that's J1 and J2. And then the rows are just M1 and M2.
Yeah. And so like therefore it's just like similar thing but different one because we have like different dependencies on row and columns. So like our rows and columns here are dependent actually, right? And in Chris's example, they are independent.
Right.
Yeah. So that's just, to me, it's just another thing to think about.
So, well, the connection that I was hoping to make is that anything that is not included in this table is not a total spin state. Like, what I mean is that if you can't break it up in this way, then J and M are not well defined for that state. And I think that's the example that Chris gave of like not being able to decompose them, because being able to decompose them means that it is a total spin state.
Yeah, but like those states at the middle, they are not decomposable. So those are Bell states actually. With the amplitudes 1 over square root of 2.
That's right, and so I suppose. Apologies. Yeah, I'm trying to think through this in terms of the matrix example, but I think I'm failing to do that here. What I was hoping to do is relate this to like whether or not these actually represent total spin states.
When you say total spin state, you mean something that's decomposable?
Yes.
Yeah, so
Okay.
I think it's basically about the different values for like J capital, right?
Right.
And in this case, we have just like J capital fixed to 1, and it's just sum of 2 by 1/2.
Yeah, like I can see the top left and the bottom right, what you call like total spin states. Those are decomposable, sort of, and then the ones in the middle, like they're not. I don't know. I think I really need to review the Klepsch-Gordon stuff because I didn't get it the first time around.
Okay, so I think we're actually getting somewhere here in that. So the rows here are Bell states, at least in the middle. The
In
two
the middle,
rows in
yeah.
the middle.
Yeah.
So these are the Bell states, and you could see that the Bell states are actually combinations of total angular momentum states, right? In order to write the Bell state, you have to write it as a combination of a total J equals 1 state and a total J equals 0 state. So this conveys the idea of like not being decomposable.
Yes. Yeah.
Whereas the ones that are not Bell states, like the ones with the coefficients 1, those are easily decomposed in terms of total J states.
Whoa. it's I just not no. I've noticed what you've been talking about the total J, and for the first time I've noticed that 0. I mean the second column and 0 at the top, and I've noticed that if you think of those amplitudes without square roots, it seems that they represent the actual spin values, like for particle 1 and particle 2. And then like second column in the matrix have like under the sum operation, sum 0, like total spin 0. And the same way the first column has total spin 1, and it repeats the first elements of the columns, right?
Yeah, I see that. Yeah, this is a very subtle point that I'm trying to make, and I apologize it took me so far to get here, but yeah, I was trying to relate this to the decomposability.
That's really subtle because I always been seeing square roots there, even if those are missing, because I don't know, I just kind of adjusted to seeing square roots. But yeah, if for some reason we can think about those 1/2s without square roots, it's kind of interesting because we can sum up those into the values of J and M somehow and try to decompose those into those like tables for m values and total values for j and m. Yeah, so there is some kind of decomposition here happening also, it seems.
So I think one last connection that I wanted to make with this is that the first and the last ones where the only coefficient is 1, I think this would be the space of the direct sum of the Hilbert spaces. But the intermediate coefficients, the ones in the bigger table here, these are actually states that don't belong to that direct sum space. They actually belong to that tensor product space.
Mm-hmm. But that's kind of expected. That's kind of expected here.
Right. Yeah. Maybe it's simple, but I just wanted to point it out explicitly here.
Uh-huh. I think that's a good exercise to sit and to meditate a bit about that question somewhere on the next week.
Yeah, sounds good.
Okay.
Thanks for bearing with that.
You're welcome. Yeah, it's interesting, but and I think I got your point, but to understand it better, I think we need more time. We need more time. So thanks for the introduction anyway. So let's finish with the material of this fourth sub-chapter here. Yes, so what we have further is the statement made by Penrose here that we also conclude that, like from all of these, that the joint probabilities for the like yes, 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 no, no, yes, and no, no results, if we kind of separate those by agreement, like no, no, and yes, yes are agreement states, and yes, no, and no, why are disagreement states. And if we combine those with the value given for the probability in the 22.9, where we have had like something like we were measuring one spin over some direction, and the state was in other direction, we have some angle theta between those, then we know that probability of measuring the result like 0 here, for example, is cosine squared theta over 2. And why is that? I have posted the actual explanation to the chapter 22 channel yesterday. So basically you can see that it comes from the Bloch spheres state representation and using spherical angles instead of complex amplitudes for the quantum mechanical states. And trigonometrically, it could be represented as 1 plus cosine theta divided by 2. And it also connects to the another example from the 22.9, where we had this thing. I'll just show you for the viewers of the video later, like this example. So this example is related actually, and I also explained it in the channel 22 yesterday. So basically, if you have like a state perpendicular here, then the overall probabilities to measure up or down will be equal, and will be equal to 1 over 2. And if you come closer using that angle theta to any state, for example to this one, then like part of probability will travel basically into it. And the amount of the probability is determined by the 1/2 of the cosine theta here because the hypotenuse here equals to 1 over 2, and therefore this side of the triangle will be 1/2 multiplied by cosine theta. So, and I haven't yet understood why joint probabilities for agree and disagree will be the same with the results of the 22.9. I will think more about that later, so I just want to make it explicit and calculate those. But anyway, they will be described by the similar formulas. One basically is sine squared of theta over 2, and other one is cosine squared of theta over 2. Yeah, and if we believe in those formulas, if we believe into those, that's like the one question: why are those correct for the Bohm setup? If we believe into those, we can now consider steps example. And steps example is described here at the top. So we have the Bohm EPR system here, particle going to the left, particle going to the right, and we have two detectors, and we have like two possible direction to measure spin here, like up and right, and here those two are like left top and right top direction. And we see that for different combinations of those directions, 4 combinations in total we will have 3 of those with angles with angle between them being 45 degrees, and only one with angle being 135 degrees. And this will be the case when we will have right the direction on the left detector, and here we will have this one like left top. So by using the formulas on the top, those two, we see that in the 45 degree cases, we get a probability of agreement of little under 15%. Why? Because cosine of 45 degrees is like square root of 2 divided by 2, and square root of 2 is like 1.4 divided by 2, you get 0.7. 1 minus 0.7 equals 0.3 divided by 2, you get your 15%. And the same way, if you substitute 135 degree angle here, you will get like complementary basically thing, like 85% of the probability. And let us allow that the decision as to which of the 2 possible measurements that I might perform need not actually be made until the particles are in full flight. And he says that let's put everything, like separate everything in time and space, like put one detector on Titan and other one somewhere else, I don't know, like a few late years away, and the source in the middle, and let's measure for some years the stream of the particles coming in onto our detectors. And let's suppose that I have chosen the up direction to measure my at my detector, and my colleague has chosen right top direction. And after receiving a stream of similarly randomly oriented particles, they come one at a time, each being a member of the EPR Bohm pair. We will find later, after we will meet with my colleague in a few years, we can read our diaries of the experiment, and we will statistically see that a little less than 15%, we have 15% of the agreement between our corresponding results, where we have like yes, yes, and no, no result, basically. Yeah, in accordance to the above formulas, basically. So those will agree. And the same way will happen with the different configurations. If we have, for example, right and top right configuration, also like 45 degrees and etc. So let's go to the most interesting one. And the most interesting configuration is when we have 135 degrees difference between orientation of our detectors. And expectations for quantum mechanics tell us that the agreement ought then to be more than 85%. And we shall ask the question now, is that consistent with the pairs of particles providing the correct joint probabilities for each of the possible pairs of detector orientations just considered? And basically Penrose later says the key thing here that is that if a particular particle pair is going to give agreement in the 135 case, this one, then it cannot be in disagreement in all of these three cases. Yeah, and I'm still not sure how to nicely combine those, but basically he makes the conclusion that there are only three of these probabilities or different other configurations, and that will allow not more than not more agreement in this overall experiment than the sum of all of those configurations, like 50% of cases for the first configuration of our detectors, 50% for second, and 50% for third. And we have 45 agreement with when we get around to the case of these 135. But quantum mechanics says us that we should have 85% here. And that's kind of where the paradox or contradiction happens. But I'm still not sure why is it happening. So I'm planning to prove that for you for the next call. Yeah, and to think more about those joint probabilities and how to calculate everything in the BOM EPR setup. But anyway, that's the basic scheme. So the basic scheme is that if we kind of calculate everything probabilistically, we will have 45% instead of 85%, which is predicted by the quantum mechanics. And he says that some might worry that argument seems to have been phrased in terms of hypothetical measurements, but this is not important, and the key issue is that the particles have been assumed to behave independently of each other after they have left the source, and to give the correct joint quantum probabilities, whatever combination of detector settings confronts them. So basically, their quantum theory says that the probabilities are not independent there, and we have some kind of correlation. And those correlations are the exact things which will give us more probability here. And he says that we have found that these cannot be split into separate expectations for the two particles individually. And the only way that the particles can consistently provide the correct quantum mechanical answers is by being in some way connected, or holistic, to each other, right up until one or other of them is actually measured. And it seems kind of contradicting, right, with relativity, because it could happen over the light years, and therefore we could have a dependence with faster than light speed of correlation happening. Yeah, and that mysterious connection is actually what is the quantum entanglement. And no experiment of this nature has been performed over such large distances, of course, but many EPR type experiments of essentially similar kind have actually been performed. And the expectations of quantum mechanics have been consistently confirmed. And although direct quantum entanglements of this nature have certainly not yet been observed over Earth-Saturn distances, some recent experiments have confirmed Bell inequality violations over distances of more than 15 kilometers. So, yeah, it seems that we have some evidences that quantum mechanics is kind of right. But anyway, there are a lot of discussions and they kind of started with Einstein, Podolsky, Rosen paper, because Einstein, Podolsky, Rosen have seen the like dangers of the entanglement basically for the relativity theory, and they write the EPR paper, and in that paper they considered that probably there is something wrong. There is something wrong with quantum mechanics and we don't know everything. So basically they believed in what is called hidden variables theory, that particles after leaving the source, they kind of have some kind of the hidden numbers prescripted inside of the particles, or something like something which is not accessible for us and not known from the quantum mechanical theory. And after particles depart, they kind of already know what the result of the measurement will be or something. But anyway, John Bell afterwards proved or stated the Bell theorem and the Bell inequalities. And if those inequalities are violated, that no hidden variable theory could be able to explain the results because of the independence of the probabilities there, and exactly those differences in probabilities like 45 and 85% here. And for example, Alan Aspect was doing some first nice experiments for the APR pairs and entanglement, and he all of the experiments currently confirms quantum mechanics and the holistic nature of the quantum mechanical or physical systems. But anyway, there are some skeptics yet, and there are some people trying to criticize those experiments and not believing and still holding to the relativistic theory, maybe for too much. But anyway, so it's really interesting to debate later. And I have sent to the channels of the chapter 23 interesting overview by the John Bias of the overall historical perspective for those EPR stuff and entanglement. So that's it for today. Maybe you have something to add to my questions, about those probabilities, how to calculate those, or maybe about those probabilities 45 and 85. Maybe you've seen something similar previously, because I never seen steps example before.
I just added a link about the entanglement distance, that try this over much larger distances now between satellites, and you can read more about it on the link if you like.
Yeah, thanks. Interesting. Mm-hmm.
More than 1,000 kilometers.
Yeah.
And they have already conducted the experiment and they confirmed the violation
I think so.
Practical quantum cryptography. Oh.
It could be useful for a quantum internet.
Yeah. Really secure things, which can be hacked only using quantum computer. Quantum hacking.
Well, I think the nice thing about quantum cryptography is that if you measure a state, you destroy that state, right, through an R process.
Mm-hmm.
So if you try to intercept a signal between two people,
mm-hmm.
well, you've destroyed the signal, and the guy will know that you've tried to hack them.
So there is no third party hacking there. But there is some kind of a gentle measurements things or something. I heard about those, which could preserve the state somehow, but yet you can get some information. Okay, so I think that's it for today. I will concentrate on those two questions about the probabilities here and those correlations and independent things between different orientations for the detectors for the next time. And also, I think we will read one more example by Hardy, and maybe a few next subchapters for the next time. So, yeah. So that's it. Do you have something to add, to say?
Yeah, just if someone wanted to mention something about geometric unity, maybe Joe had a look at it.
No, I wasn't watching.
Too much? Oh, okay. Yeah.